If you think that you understand quantum mechanics, then probably you haven't understood anything at all.
I would like to welcome you all to the very first seminar that we're holding this year as METU Physics Society. Thanks to our dearest Professor Sadi Turgut, who kindly accepted to spend their evening with us. I once again welcome you all and leave the stage. Stage is yours.
Thank you very much. All right, thank you very much. Well, let me first of all say this, right? This is a talk that I have given in Turkish on last Friday. So it's going to be a repetition, but this time in English. So I have changed everything, tried to change everything to English actually. It's more or less the same thing, right? So if you have gone there, if you have watched that, probably you're going to get bored. There will be only a few things which will be different, right? So it's going to be kind of an explanation of what this year's Physics Nobel Prize is about. It's about quantum theory first. But specifically about the entangled state. So these are very important concepts nowadays, technologically as well. Unfortunately, it's something that's quite difficult to explain, right? I'm giving this 455 course, Introduction to Quantum Information Theory. We actually cover more or less these kind of things. I mean, the topic that I'm actually going to explain will be more or less some part of that course actually. And I have difficulty in explaining what's going on in there. So as a result, it's natural that I have a difficulty in explaining this without using any equations and things like that. But I'm going to use an equation, right? In any case, so the subject is like, there's a nice word in here, reality. All right, so as a result, with these words, it might appear like this is a very significant thing. Well, it is in some respect, but just keep in mind that in science everywhere, when we use a word, we use it as a term, right? And we usually define it in a certain way. So when we say reality, we just define reality in some certain way. And that's basically that story. And it's not... probably you should not actually confuse it with the word reality that you use in your daily lives, right? So I'll explain what reality is. So basically it's just a struggle in a way. It's a match between quantum theory and some realistic theories. And it appears that this match is won by quantum theory, all right? So that's the conclusion of that talk. So in any case, well, it's some research that has been done in the past. It's like I don't know, it's like 80s means like at least 40 years has passed since the experiment. But of course, Nobel Prize is not given on a timely fashion. So they are giving it in this year, right? So in any case, there are these three experimentalists, Clauser and Aspect. They have done some experiments on testing Bell inequalities. This is basically what I'm going to explain. Zeilinger also has done some experiments on Bell inequalities. He has done some important work on it. There are these like GHZ states, for example, which bears his name. In any case, but the prize is given to him for his, I don't know, some again experiment that demonstrated something called quantum teleportation, right? So I'll also try to explain what this means, again, without using any justifications or anything like that. So I'll try to explain what that thing is. Okay? So entanglement is the key words in, one of the key words in here. So I'll also talk about this. Okay, so summary. There's some kind of a historical background in here. So the prize is about the quantum theory, right? It's not about the application of quantum theory. There are many prizes like that, actually. But it's about the the nature of the theory itself, right? So I'll try to make this connection in a moment. So when I'm writing this thing down in a hurry, I make lots of mistakes. So just forgive my mistakes. So that's a quantum theory, of course. So in any case, it's like the story of quantum starts at the 1900 with Planck's work. In 1925, it's completed by Heisenberg's work on matrix mechanics, whatever that is. But in any case, I mean, in these years, Heisenberg and Schrödinger essentially formulated the quantum theory that we know, right? So the quantum theory that we are using today is actually done in that year. And then in the next year, there's 27, there's a famous Solvay conference. I'm just going to say a few words in here. But there's this problem of interpretation arose in there, right? So basically we have a theory, a perfect mathematical machinery, but we don't understand what it says, essentially, right? We don't really comprehend what it is saying. And in this conference, they have actually discussed this truly. Unfortunately, they couldn't solve the problem. And so as a result, this problem continues even today, right? You can sometimes see some articles published in this interpretation, that interpretation, and whatever. Most of it is actually philosophical discussions. In any case, so I mean, our story actually starts after that. It's like there's a very key paper in 1935 by Einstein and two of his students. It's an EPR paper. There's some kind of a case in there, and they also introduced this entanglement idea in there. In any case, so they basically suggested that the quantum theory is a bad theory. Well, it is incomplete, right? I'm going to use their words. It's incomplete, so we have to find a better theory that explains nature in a better way, right? Perhaps something like that. And after that, in 1964, John Bell actually shows that some of the ideas expressed by Einstein can actually be tested experimentally. Right? It's a theoretical work, actually. But he said that, well, I mean, to decide on that question, we can actually go to the lab and test it. And these two people have tested them and found that Einstein was wrong. There was actually a talk in the past, like 10 years ago or something like that, that I have given in here, in Turkish. Bell against Einstein or something like that. Probably this is somewhere, but I don't know where. In YouTube, perhaps. I mean, this is more or less, I don't know how I explained it there, but yeah. In any case, let me also say this, and there are lots of sayings which are kind of parallel to this. Quantum theory conceptually is very hard to understand, and so as a result, I mean, if you don't understand anything, then don't feel bad, all right? That's what I need to say in here, perhaps. I'll try to do a good job in here in explaining, but still, I mean, some of the concepts may, I mean, we will be talking about lots of concepts, and that's the main difficulty, I guess. So as a result, if you have some questions about something, then you can actually stop me and ask the question, all right? I mean, let's go like this. So this is actually quite famous, but I found out that probably nobody said it. So it's attributed to Feynman. If you think that you understand quantum mechanics, then probably you haven't understood anything at all. So we are more or less, most of us are in this position actually. I'm going to talk about lots of concepts. Realism is one of them. Locality is one of them. And then locally realistic theories. There are some other names like hidden variable theories and things like that. Probably you know about uncertainty. And well, there is this compatibility and incompatibility thing. So all of them have to be mentioned somehow to actually explain what's going on in here. All right, I'll start with realism, but I'm going to postpone the other ones later. But some of these are the things that you actually learn in quantum mechanics courses, like compatibility. Compatibility, no problem. We say that in quantum mechanics, for example, if two observables commute, then they are compatible, right? If you have taken 431, or I don't know, 300 perhaps, it's the we mentioned in there. I need to mention all of them in one way or the other one, but probably you won't be able to understand everything in there. Okay, so the question is this. When you are measuring something, like current, for example, or position of a particle, or something like that. Here I said x. When we measure a quantity x, and we get the value, let's say x equals 5 without units. What's the meaning of that value? All right? Normally, normal students actually understand it like that. Before the measurement, this quantity had this value 5. When we measured it, we learned that value, right? For example, you have a circuit, there's a current in there. You measure the current. Before you measured, of course, the current had a value. You just learned that value, which is reasonable. But the quantum theory says, well, no, that's not the case. Before the measurement, I mean, this is true for most of the cases, but there are some situations where which cannot be described like that, but for most of the time, right? Before the measurement, the quantity was uncertain, right? We say that there is an uncertainty in it. It did not have any definite value before the measurement. So what happens is that during the measurement, something happened. We don't describe what and how and things like that. Something happened and its value became certain. And but it became certain at a randomly chosen value, which is 5. So as a result, before the measurement, the value of x is meaningless. Only after the measurement, the statement that x is equal to 5 has a meaning, right? So this is actually a different point of view. So let's say that x has like other possible values like 3 and 4, for example. So there might be some situations where before the measurement, x might have all of these 3, 4, and 5 values at the same time, right? So as a result, it did not have any definite value. So as a result, when you do measure the value of x, well, you cannot get all the possible answers. So you must get only a single answer. And what happens is that in the measurement process, somehow something happens, and all of these other possible outcomes, 3 and 4, are eliminated. Only 5 is somehow realized and whatever. Okay, so that's the first thing. That's one of the things that students usually do not understand when they see quantum theory. All right, you're not learning something in the measurement process. So in the measurement, so somehow you're interacting with the system somehow, one way or the other way. You're interfering with the system, and so as a result, the system changes. And as a result of that change, the thing that you are measuring becomes definite, right? So there's this kind of a process, right? So as a result, this is actually quite hard to understand. This is quite reasonable. So this is our classical worldview, essentially, right? There is something there, and we are learning it. So when we say, well, when we think that there's a quantity has a definite value, we are going to use the realism associated with this kind of a situation, right? Again, our classical world is realistic, all right? So there's some kind of a reality, even if we don't measure it. So for example, I don't know, I know that there's, for example, some cars outside, for example. I'm sure that there are some cars there at some certain locations. When I look at them, I'm measuring their positions, right? But I'm measuring the positions that they already have. But the quantum theory says that, well, the cars are not there. Well, probably cars are everywhere. And then when I'm looking at it, somehow I'm making them actually collapse to some kind of a state or something like that. Okay. All right. So there are these 2 points of view, right? The quantities have a definite value, and we measured it before the measurement. Sorry. But the quantum theory says that, well, they don't have a definite value. They are uncertain, and somehow we are changing it. Okay. So the question is, right, how do we understand which of the above statements is correct? Classically, we know that this is the correct one. Sorry. I mean, we know that this is the case, but perhaps there might be some doubts after seeing the quantum theory. But in any case, at least for some quantum phenomena, it appears that this is kind of necessary to explain some certain things. So I'm going to give the double slit experiment as a justification for this kind of a point of view. I'll try to explain why this is the case. But still, I mean, there were attempts to explain these kind of experiments by some realistic point of view, right? So there are actually 2 different theories in here. One is the quantum theory. Well, it's basically the mathematical quantum theory, right? Let's see it like this. There is a mathematical theory there. There are some symbols in there, right? There are some things that we call as wave functions and things like that, right? And when we just look at these symbols and the numbers and things like that, this is the thing that we understand. And so as a result, we think that this is the correct picture of what's going on there. All right? So that's a theory. That has to be a different theory. That's not what quantum theory says. So the realistic theories are something else. So there are 2 possible theories, actually, that we can actually use. Is there really a realistic theory? Yeah, there's one example. It's called Bohm's hidden variable theory. It's actually a theory that explains all of these atomic quantum phenomena, let's say. And it explains perfectly. I'll talk about it actually later. There might be some other theories as well. So as a result, we don't rule them out. But we usually talk about all of the possible realistic theories. Okay. How can we understand which of the above is the correct one, correct description of what's going on? I mean, is there a reality basically for the value of a quantity that we try to measure before we measure it? Or is it uncertain just like the quantum theory says? Okay. It looks like a philosophical problem, which means, I don't know what that means. For me, it might mean like you can discuss it, I don't know, 2 hours, 5 hours, 10 days, but at the end, you don't actually pick one solution, and everybody goes to home and everybody's happy. Nothing happens, right? It's basically a discussion on, I don't know, on this words, in the level of words, let's say, right? Or in the level of basically the theory. So in that case, this question does not need to have a definite answer. But it turns out that that's what Bell has shown. We can actually distinguish these 2 different points of view. And we can distinguish by the scientific method, right? We can go to the lab, do some experiment, and the experiment tells us that, well, this is wrong or that's wrong, all right? So as a result, then we can pick the other theory. All right, so that's basically what it is. But how Bell actually shows this, the idea is something like this. So do I have, yeah, I'm not going to write anything on the board, all right. So suppose that there are lots of quantities that we can measure, like I mentioned X, but let's suppose that there's Y and Z and whatever, right? There's this compatibility thing in here. So it appears that we cannot measure all of them at the same time. So at a given time, I can measure only a few of them, all right? So we cannot learn all of them at the same time. But so as a result, quantum theory says that, well, all of them cannot be definite at a given time. So as a result, yeah, it just stops there. But the realistic theory says that even if I don't measure them, they have a certain value. And so as a result, I can write down some kind of a mathematical expression involving all of them. And perhaps these mathematical expressions satisfy some inequalities and things like that. This is essentially what the story is. So basically, the realistic theories claims that they claim that these quantities actually satisfy some certain relationships between them. These are called Bell inequalities. And somehow it appears that the quantum theory does not satisfy these inequalities. So there are some certain relations where all realistic theories must satisfy. Some realistic theories must satisfy. And it appears that these are violated by the quantum theory. Right? That's the whole story, actually. Bell has shown that this is possible. And they have done the experiment, and they have shown that the quantum theory appears to be actually better than the realistic theories in describing the nature. But I'll try to explain some of the details. So, right, this is quantum theory. It kind of shows how difficult it is, right, this table. So this is just a list of Nobel Prize which is given for the development of quantum mechanics. I think there are like 13 Nobel Prizes in here. So that's actually a nice book that explains this history at that time. Most of the story in here. So in any case, I mean, it's not something like theory of relativity, for example, which is discovered by one person only, or the general theory of relativity, for example, which is discovered like in 1 year or 7 years or something like that. It took like 25 years with many people. And so as a result, only at the end we have like some kind of a theory that nobody understands, right? So in any case, this year's prize can actually be considered as the 14th prize given to the development of quantum theory, because it tells us something about the theory. So basically, Heisenberg and Schrödinger have written down the mathematical theory. Max Born came up with this probabilistic interpretation. All right, so what we know is that, of course, this theory is necessary for atomic, molecular, and subatomic physics, particle physics. But somehow we also know that, we are convinced that this is also true for macroscopic systems. So there are like large systems of millimeter size, which is quite macroscopic actually, compared to the atoms, which basically behaves quantum mechanically. All right? So we are actually, most of us believe that this is also true for even larger systems as well. For us, probably. And some people think that the whole universe is in a quantum state, actually. Right? So, but because of some reason, somehow this quantum behavior disappears on our level, and we just see a classical world around us. Right? Again, it is hard to explain why this is the case. So somehow we cannot see the quantum behavior around us. That's an important detail which appears to be very important. So quantum theory is successful, very successful. There's this G factor of electron which has been measured with like 10 digits of precision. Like it's a precision of 1 in a 10 billion or something like that. And it can be measured, but it can also be computed by using quantum theory, and they perfectly match. Right? That's actually a very nice indication that the theory is very good. At least the mathematical theory is perfect, actually. It's just that nobody understands this, right? That's the only problem. That's something that is kind of famous. Like in 1930s, 40s, students are told to shut up and calculate. So they were questioning about the interpretations of quantum mechanics, and their advisors told them to shut up and keep computing, because at the end, when you compute something, right, you can publish something, you can find something, but the interpretation is that's in Turkish, right? Interpretation is problem is something that cannot be solvable. All right. So some things are out of order, right? 1927 Solvay conference. They discussed the the interpretation problem in detail, but they couldn't decide on this. So most of the discussion is between Einstein and Bohr. Einstein was actually saying he was actually objecting this uncertainty thing. There were actually several objections made by Einstein, but somehow Bohr was able to answer them, right? So people think that Bohr actually somehow won this this match. But in any case, nobody thought that this is finished. So de Broglie is somewhere in here. No, sorry about this. Yeah, I have a problem with people. All right, I'll talk. I'll show a different picture later. All right. In any case, but Einstein was actually still kept thinking about this kind of a problem, and later in 1935, he came up with this argument. So this is the double slit experiment, but it is carried to our macroscopic world so that you can actually understand what is wrong in here clearly, right? So the experiment is something like that. This man is a blind man. He doesn't see anything. But he wants to actually use this polygon, right, for shooting exercises. So there are actually two windows in here, and there are some targets in here. So he just fires his gun randomly, and many times, in fact, and then of course after that we just count the number of holes in the targets. All right, that's more or less the experiment. You can actually think of it like that. So there are two windows in here, but we just first do this experiment with one of the windows closed. So only this window is open. The bullets can only pass from that window, and when this happens, when we observe the targets, we actually see that the bullets actually hit all the targets in a uniform manner, let's say. All right. All right. This is actually called what we call as diffraction, actually. But I don't want to go into these kind of details, actually. But let's just discuss the experiment, right? When the bullet is passing through that window alone, it can end up with all of these 4 targets. If I open the other window and close this one, and do the experiment again, we more or less get the same thing, same kind of a distribution. All right? But if we open both of them, in that case, something curious happens. This time, these 2 targets do not get any hit. And the question is, how do you explain this? It doesn't have any classical explanation, all right? So as a result, we have to come up with some kind of a strange explanation to try to explain this, right? That's essentially what we have been doing, right? In any case, so the idea is that this is the naive idea, actually. When a bullet is fired in here, it passes from one of the windows, and in that case, if it is passing from the right window, for example, in that case, I would expect that the result is the same as the bullet, the experiment done with only the right window is open, right? But somehow, it is not. So as a result, when the bullet is passing from this window, it somehow knows that the other window is open, and so as a result, it doesn't end up in here. It knows somehow that it shouldn't end up in here. I'm not giving some personality to the bullets, but this is actually one way of explaining it, one way of stating what the problem is. Okay. Of course, we don't do this experiment with real bullets, so it's hard to do it. There are some problems in there, but we can actually do it with particles. You learn that this is, first of all, is done with photons for the first time. Then it is done with electrons, and then after that, people actually have done it with molecules and things like that. So this is like more or less a modern experiment. they have done this experiment with a huge molecule. Actually, it's like a molecule with about 500 atoms. It's huge. Probably you can even see it in a, I don't know, in a microscope perhaps. It's a well-developed microscope, right? So as a result, there is no discussion in here whether these are particles or waves, all right? So in any case, if one slit is open, you just see only the diffraction pattern in here. But if both slits are open, then you see an interference pattern. And the question is how a particle can show such a behavior in the situation. Okay, so the usual explanation is that, well, the particle behaves like a wave in here. So a wave can pass from both of the slits, no problem with this, and then a wave interferes. So there's destructive interference in here, so that's the explanation. But still, this is a particle, right? I mean, how do you understand the wave-particle duality? So as a result, if you actually pose the problem with a macroscopic object like a real bullet, that becomes really ununderstandable. I mean, perhaps you can understand this for photons, but for large particles, it's hard to understand. Okay, so in any case, in quantum theory, we say that, well, basically the equations tells us that the particle doesn't pass through a single slit in here, it passes from both of them, which is actually quite hard to understand, right? But it's actually the uncertainty concept is at play in here. So if you think about the slit that through which the particle has passed through as a physical quantity, for example, this quantity is uncertain, right? The slit that it passes through is uncertain. So the uncertainty is somewhat essential in here for this behavior. Okay. So this is actually an interpretation, but lots of people actually, lots of people nowadays actually follow this kind of an approach. So there's something called the Copenhagen interpretation. This is the interpretation favored by people around Niels Bohr. Niels Bohr was Danish. He was in Copenhagen. So as a result, because of that reason, this is called the Copenhagen interpretation. So probably these people didn't actually explain it like that. They instead say it like, well, the slit that it passes through is uncertain. We cannot give a reality, perhaps we cannot give a real meaning to the slit that the particle has passed through without measuring it, right? Probably they said something like that, and when they say it like this, well, Einstein probably objected even more. So in any case, basically, I mean, this is more or less consistent with the Copenhagen interpretation, but that's the one that I prefer actually. So it's a different kind of a behavior. A particle can pass through two different places at the same time, and that's the reason why the particle shows a different behavior in here. So in here, particle passes from one slit only, that behavior. It passes from both slits at once, somehow, and it shows this, this behavior. So that's actually a nice YouTube video. I mean, all of these experiments are done like that. It's actually the behavior of a single particle, but I mean, essentially we send the particles one by one. So as a result, when we actually look at the collective pattern formed, only in that case we can actually notice the interference pattern. But a single particle, when sent through this double slit thing, it doesn't end up in these what we call as dark fringes. They don't end up in here. But you don't notice these fringes for an experiment done with a few particles. So you have to repeat all of these experiments many times. You may want to look at this. I don't know, it's actually a very nice thing. Uncertainty, therefore, is an essential feature of quantum theory, right? Some quantities have to be uncertain. You know the atom, right? We actually describe it with some kind of a cloud or something like that. What is a cloud? It's a probability cloud. But in there, the position of the electron is uncertain. Their velocities are also uncertain. Here, the slit in which the particle passes is uncertain, right? It's the same kind of uncertainty, actually. But it's the uncertainty in a different quantity. Here it is position as well, right? Yeah, it's the uncertainty in position, basically. But we actually meet these kind of uncertainties in many ways. So this is how we would actually show the quantum state of the particle passing through the slits. It's in a state where it is passing from the left and the right at the same time, all right? What's the meaning? Well, that's some kind of a mathematical expression. It turns out that in quantum theory you are going to learn that, well, it's not just plus in here, there are some numbers also in here. So there might be some phase factor in here. So that sign, for example, might be negative, in which case you get a different quantum state. It's still a state where it is passing from both left and right slits at the same time, but it's different in some respect. Okay. So, yeah, whatever. But the realistic view says that, well, it says that this is nonsense, right? It says that the particle passes from either the left slit or the right slit, but we don't know which one, okay? But, I mean, it is saying something else. And also in here, for the electron, right? Electron is somewhere in the atom, but we don't know where. This is the realist view. Right? So sometimes when we try to understand what's going on inside the atom, we actually say this. I know that some students say it. Electron is somewhere, but we don't know where it is. So it kind of tells us that it is we are to be blamed for not knowing where the electron is. So it is somewhere, but it's our ignorance. But the quantum theory says that, well, we are ignorant, that's true, but the electron also doesn't know where it is. It itself doesn't know where it is, right?
Sure.
Yeah.
Then how does this view explain the double slit experiment?
How do we explain?
How does the realistic view explain this experiment?
Yeah, there's some kind of a theory that I'll explain. It's like the de Broglie's pilot wave theory, Bohm's theory, actually. Yeah, when time comes, I'll explain this. So in any case, what happens if I actually remove this uncertainty by doing a measurement, right? This is basically before and after. If you do a measurement, then you discover through which slit it is passing through. And in that case, the slit it passes through becomes certain, and so therefore the quantum state should also change, right? So somehow by our interaction with our measurement, our interaction with the particle changes its quantum state, and so therefore it changes the experiment. And in that case, it appears that if you measure the slit that it passes through, in that case the result of the experiment should also change. Okay? So that's one of the things. This is the famous, sorry. Yeah, that's the same thing, yeah. That's the famous which path experiment, Verscher-Weg or something like that. Experiment. So the idea is this, right? If you don't measure in which slit the particle passes through, you see the interference pattern. Again, I mean, you see the interference pattern after collecting millions of particles, all right? In any case, but you can try to measure the slit from which the particle passes through. The method that's proposed by Bohr is to place an atom in here, an extra atom, which is at rest, let's say, or more or less at rest. When the particle is passing through this slit, for example, it might hit the atom and push it forward, let's say. And in that case, by looking at this motion of the atom, you can understand that the particle has passed through that slit, for example. And if you don't see any moving atom, then in that case you would say that probably the particle has passed from the other slit, right? So that's one way of actually measuring the slit through which the particle has passed. past. So in any case, board uses this and does some discussion, but at the end, this interference pattern is disappeared. Okay? So if the slit is uncertain, if there's uncertainty in here, you can see the interference pattern. If the uncertainty is removed, then you're back to the original result, right? If you know the slit that the particle passes through, you just see this diffraction peak only. You don't see any interference, which is kind of consistent, right? So what? So that's the collapse of the wave function thing. All right. Sorry about this. I need to do this. So that's actually a nice analogy, right? That kind of explains what we mean by this state in the quantum state of the particle when it's passing both slits. So suppose that there are like some kind of a universe and there are some creatures in that universe, but these creatures have seen all the lines around themselves to be either horizontal or vertical for some reason, let's say. I mean, we're just imagining things, right? In their whole lives, they have seen only horizontal lines or vertical lines or line segments. Okay? So as a result, when these creatures actually see a slanted line like that for the first time, they won't understand it, right? They will have some kind of difficulty in understanding it, probably. Definitely they will have a difficulty in explaining. So that's our difficulty with quantum theory, right? We have lived with the classical world around us, and so as a result, whenever we see a quantum, phenomenon, like the superposition state in the double slit experiment, we have difficulty explaining it and understanding it as well. So we are kind of in a same kind of a situation, okay? And I'm just saying that probably these creatures are going to call the slanted line as a line which is both vertical and horizontal at the same time. All right? When I say that this particle passes from both slits at the same time, we are actually talking about something like this. So in that case, the particle is in some kind of a quantum state, which we cannot comprehend actually. And the best thing that we can do to describe that quantum state is to describe it as a state where the particle is passing both from the left slit and the right slit. Okay? But just keep in mind that there are many slanted lines in here which will be described in the same way. So there can be many quantum states that we would actually describe by saying that whatever. But they will be different, right? So as a result, our words are not able to describe what's going on in there, actually. Kelimeler kifayetsiz, right? Then quantum theory is actually is at play, then we cannot do this. So, yeah, that's basically what's going on in the double slit experiment. So there's some kind of a certain quantum state in there. It's a superposition state. We call this as a superposition state. Whatever that is, that's something that we cannot, in our brains, we cannot understand what it is. But the only thing that I can do is that, well, I just trust the mathematics. So if I'm able to write this thing down, I know that this corresponds to some kind of a quantum state. It has some unique properties. I don't try to understand it, but I just use mathematics to deduce what are the results that, if we do some certain experiments, what kind of a behavior this thing actually shows. So the interferences, for example, is the behavior that we get for the double slit experiment. Schrödinger's cat is another example of it. Schrödinger actually has shown this, so you can put a cat into this kind of a superposition state. Again, just keep in mind that it's not a state where the cat is either dead or alive, but we don't know which one. It's not that state, right? It's not this realistically interpreted state. It's a state where the cat is both dead and alive, right? Again, it's hard to understand what that thing is. if I put a minus sign in here, it would be a different quantum state that would be described by the same words again, but again, it's something else. It is easy, yeah, that's in Turkish now. It's easy to put a cat into that state, but it is quite difficult to prove that you have done this. That's actually quite difficult. So we cannot do these kind of experiments, but there are things like macroscopic systems where we can actually put them into these kind of superposition states, and we can prove that. The key is something like that, right? This superposition thing, this interference thing. So whenever we see an interference pattern, then we understand that when the particle is passing through the slits, it is in this superposition state of passing through both slits at once. All right? When we observe this interference, that's a proof that it is in a superposition state in here. Otherwise, if it's passing through one of these things, it's not in a superposition. Okay? So we can do this for this particle or for many quantum systems, but with a cat, we cannot do an interference experiment. That's the difficulty with the cat. Right? So as a result, the Schrödinger's cat is still a thought experiment. It's not a real experiment. But I heard that there are people they would like to do, for example, this double slit experiment with real live viruses. It's something, right? Well, it's kind of alive. And can they do it? I believe that they can. And there should be no problem with this. Okay, so compatibility. I said that I'm going to mention about this, but you somewhat know perhaps some of them. So in any case, if you have like two observables, these two according to quantum theory, can be compatible or incompatible, right? When they are incompatible, these are like the position and momentum of a particle. In that case, one of them must be uncertain. So if you determine the position, for example, the momentum would be uncertain. Or if you determine momentum, position would be uncertain, for example. So there's some kind of a mathematical relationship between them, so that if you somehow measure one of them, then the other becomes uncertain, right? So as a result, we just call these kind of observables as incompatible. There are many examples of these. I'll tell you one more example. So they have this kind of a behavior. Basically, you cannot measure them at the same time. All right? The reason is that what I have told you. Right? If you measure one of them, then the uncertainty decreases for that one. So the uncertainty for the other one must increase. Okay? So these are things that you cannot measure at the same time, right? So the quantum theory tells you this. There are some certain things that you cannot measure in you can only know one of them and not the other one, right? Probably that's the better way of saying it. But there are also some compatible quantities, especially, I mean, if you have two particles, for example, any property of that and any other property of the other particle, they are compatible. You can measure them at the same time. They can both be definite. No problem with this. All right? Both can be certain. You can measure them at the same time. No problem. I mean, some quantities you can actually measure at the same time. And you can measure first one of them, then the other one, or the other way around, or both of them at the same time. All of these measurements actually produce the same results. No problem with this. So as a result, usually we are not also interested in these kind of details. So which one you measure first, or things like that. These are also irrelevant. Why did I talk about this? Because somehow I have to. Okay, so in any case, so Einstein knows that he has to object to uncertainty in quantum theory. So he tried to prove that the uncertainty actually should not exist. So as a result, he concentrated his efforts on this one. Determinism is also lost. there are lots of probabilistic arguments also entering into the picture as well. So I think I have described this, right? Realism. Okay, so I'm repeating the same idea again. All right, but let's just repeat it again. So quantum theory says that, well, as long as we do not determine the slit it passes through, the slit it passes through is meaningless. Yeah, whatever. I mean, I can quantify this. Instead of talking about the slit that it passed through, I can say that when it passes through the left slit, my variable quantity is equal to -1, and otherwise it is +1, for example. So in that case, instead of talking about words, I can use variables in here. So the quantum theory says that at least in the double slit experiment, X is uncertain. So as a result, we cannot measure any value to X before measuring it. But the realistic theory says that, well, it has a definite value, but we don't know which one is it. All right, that's a quote from Einstein that people repeat it, but this it's actually kind of interesting, right? So Abraham Pais is a physicist who actually wrote some biography of Einstein. Lord, what? Yeah, I forgot the title of the book. In any case, so when they were talking, of course, at one point, Pais was a student of Bohr, actually. So they were discussing about these interpretations of quantum mechanics. So at one point, he stops and says, well, do you really believe that when you don't look at the moon is not there when you don't look at the moon, right? So, I mean, at least the quantum mechanical interpretation is that if we look at the moon, we measure its position. If you don't do this, then its position is not measured, so therefore there's some kind of an uncertainty in there. In any case, this is actually a problem which is expressed in macroscopic terms, right? I mean, this is a very reasonable question, actually. It's not the existence of the moon, but it's really the position of the moon. So the Copenhagen interpretation kind of says that the position doesn't have any meaning if you don't measure it, right? That's basically what they are saying. When you express this not for an electron but for the moon, it kind of becomes meaningless. But we know that at least for the moon, I mean, the size of the uncertainty for the position of the moon should be very small, actually. It's experimentally undetectable. But still, I mean, if you want to express it like that, it's... what is interesting in here is that if you remember, there's actually a very old philosophical problem from the time of Greeks. If a tree fell in the forest, but there's nobody to hear it, will there be a sound, right? That was one of the famous questions of old philosophers. What they were actually trying to understand is the nature of sound, actually. I mean, does sound have a physical reality which is independent of the person who is hearing it, right? That's the question. So now we know that, well, the sound is basically the vibrations of air molecules. So yeah, it exists without somebody hearing it, without the existence of somebody hearing it, right? This is more or less the same kind of a question, actually, but it asks about the reality of the quantities, values of quantities. But in any case, I don't know. I mean, I find this actually quite strange. So EPR, that's how we know this 1935 paper by Einstein, Podolsky, and Rosen. They propose some kind of an entangled state. Entangled state first enters into the picture in this article. It is 1 hour now. So we can continue until 12 o'clock, for example. All right? So be prepared for this. All right. Entangled states first enter into the picture. So these entangled states actually satisfy some some certain properties, right? They display some strange behavior, let's say. By arguing on that behavior, they actually claim that the quantum theory is incomplete and somehow we have to incorporate realism into the theory, right? Bohr was not able to answer in a satisfactory manner to that article. And so as a result, people thought that this is actually a very important unsolved paradox of quantum physics until like 1960s or something. Okay. But I'll actually talk about the EPR. I'll try to talk about the EPR argument. There are also things that I don't understand in there. But let's talk about the entanglement. Entanglement is basically a property of like two or more particles, but we usually discuss it for two particles. If you put the two particles in a state where their states are correlated, right? It's a very particular type of a quantum correlation, actually. So if we have a situation like two particles are crossing the slits, for example, you might think about a particular quantum state where both of these particles are somehow passing from the same slit, for example. Let's say P and Q are the particles. Both of them are passing from the left slit, superposed with both of them passing from the right slit, for example. This is an entangled state. I'm just writing this as an example. Here, there's a correlation between these properties, right? But it's a correlation of a different kind. It's a quantum correlation. Okay. All right. Historically, this is something the electron spins actually come into play later. But I'll talk about the spin measurement of spin and electron spin or something like that. All right. So let's talk about spins. Spin is a vector. It's actually angular momentum, but that's not an important detail. You can actually think of the electron as a magnet. It is, right? It actually produces a magnetic field. It carries some kind of a magnetic field producing magnetic moment inside, right? And this thing has an orientation like the needle of a compass, right? But it's actually a vector quantity. The problem is that in quantum theory, you cannot measure this spin orientation. Why? Well, it just appears so, right? You just do some mathematics and then the mathematics tells you that you cannot measure the spin orientation. You cannot measure the quantum state of any particle, actually. So that's one of the things that's kind of important. So if you remember, measurement tells us something, but in the meantime, it changes something, right? So as a result, there are some certain things that you can measure, some certain things that you cannot. It appears that you cannot measure the quantum state. You measure something else. Okay. When I said you cannot measure the spin orientation, just remember that the spin is a vector. It has three components, x, y, z, let's say. It appears that all of these three components are incompatible with each other. You cannot measure any two of them at the same time. You cannot measure any three of them at the same time as well. You can only measure at a given time only one component. And the reason is basically, all right, this is from second year modern physics course. There's an experiment called Stern-Gerlach experiment. In the Stern-Gerlach experiment, you send the electron to an inhomogeneous magnetic field, a strong magnetic field, and you choose the direction of the magnetic field. So if you choose the direction of the magnetic field along the z direction, for example, this is a device that measures the z component of the spin of the magnetic field, right? So x and y components are not measured. And since this is the only way to measure the electron spin, you cannot measure both the z component and the x component because at the same place, you cannot apply both a magnetic field along the z direction and along the x direction, right? That's the reason, in a way. So as a result, physically, you are prohibited from measuring all components of the spin. But there's also some kind of mathematical reasons why we cannot measure them, right? Okay, so I'm going to cut the story short. If you apply your magnetic field like that and use this String-Gerlach experiment to measure the spin of the electron, the device tells you one of two possible results. It tells you that whether the spin is upward or the spin is downward. That's independent of what the spin orientation of that particle is before the measurement. So spin orientation might be like this, for example, might be towards left. That's a possibility. In that case too, we either get this result or that one. And it is probabilistic, of course. If it is horizontally oriented, then these probabilities are 50-50. If it is oriented in the upward direction, we definitely get that result, for example. So in any case, okay, so therefore there are actually a set of measurements that we can make on the spin. So I don't know if you have any questions in here. I'm just going to give you some examples. If I, for example, it doesn't matter what the initial state of the electron is, we always find these results. So whatever the orientation is, just keep in mind that in that measurement process, this collapse of the wave function thing occurs, right? Just like in the double slit experiment, measuring the position of the particle gives you one result and changes the quantum state. Here, there was some kind of an initial quantum state in here before the measurement, but this is completely destroyed. All the information in there is lost completely, and after the measurement, we get either that or that. That's one of the difficulties with quantum computation, quantum technology, actually, right? You cannot measure everything. You can only measure some kind of a limited thing, and by using this, you have to do something useful. All right, so in any case, if you measure the spin along this direction, collapse occurs to either the spin to the right or spin to the left. If you measure it by some slanted angle along this direction, then you find the spin to be parallel to that or anti-parallel to that, right? So always there are two outcomes, and the spin is up or down. So this is the entangled state, right? There's a minus sign in here. There's no normalization. But there are two electrons, whatever they are. There are two electrons. If the first one has a spin up along Z, let's say, the other electron has a spin down along Z, this state is superposed with this other possibility, right? But it's a very particular superposition, actually. So as a result, you would say that at least for the first electron, the spin is both up and down at the same time. So therefore, it's completely uncertain. And for the second electron, too, the spin is completely uncertain, right? It can be anything. So this particular state is a state where the total spin is zero. And that's the reason why we are actually using it, because analysis is actually quite easy with this particular state. Basically, that means that the spin components are always anti-parallel to each other. All right, let me say this. Like, I mean, for example, when we do this, like molecular, when we talk about orbitals and things like that in chemistry, for example, when we fill an orbital with an electron, with electrons, we just pick one of them is in the up, to be in the up state, and the other one is in the down state. For example, in that particular case, this is the state where the electrons are in, right? I mean, if two electrons are within the same orbital, their spin state is this. It's completely antiparallel, and by this we mean this. And it appears that the spins of each electron is actually antiparallel to each other, yes, but antiparallel to each other in all orientations, actually. Okay. Question, sorry. This is also one of the frequent questions. How do you make sure that the electrons enter into that state? Okay. How do you entangle two electrons? It is necessary that these electrons are actually somehow interact with each other. Any interaction will actually entangle them, right? That's the answer in here. But this one is particularly easy if you somehow make sure that they actually enter into the same orbital. they should definitely be in this particular spin state. Okay. That's not the only entangled state, but that's the one that's quite easy to discuss. So as a result, we'll talk about this. I still didn't talk about the realistic explanation of the double slit experiment. I'll come there. So, yeah, that's the 40th page. Sorry about this. I need to go ahead. But, I mean, let's just talk about this, all right? So, I'm preparing 2 electrons in that state, all right? That's called a singlet state, right? I'm just going to label the electrons like that with colors. You cannot do this with real electrons, obviously, but this is just for a discussion, right? And I'm going to assume that they are separated far apart from each other. So it doesn't matter whether they are close or they are far apart. So once you put them into an entangled state, they are going to preserve this state if you are too far apart. So you can assume that the other electron is on the moon, for example, or sometimes we exaggerate and we say that, well, the other electron is at the edge of the galaxy, for example. So there are like, I don't know, 100,000 light years distance between them, for example. It doesn't matter. What the quantum state that they are in does not depend on the distance between them, right? And that's some of the things that we can actually test with modern experiments. So what we do is like, we just measure the spin of the first electron. So before the measurement, the spin is completely uncertain. So after the measurement, it's going to become definite because of the collapse of the wave function. So let's suppose that the outcome is spin up. I mean, I measured the spin, and the spin turned out to be up. In this case, the other electron in here should suddenly collapse to the spin down state. All right, that's the strange feature in here. And if we get the other outcome, then the other electron should collapse to this other state, right? So what's going on in here is something like that. There's an electron in here. There's another electron on the moon. I do a measurement in here. Because of that measurement, the quantum state of that particle changes. And at the same instant, the quantum state of the particle on the moon also changes, right? At that instant, suddenly. So whatever I have done in here somehow affects the other electron. I'm essentially, when I'm measuring the spin of that electron in here, I'm interacting with it. I'm applying some magnetic field on it, for example, right? I interact with it. I somehow change the state. So that's understandable. So this collapse is understandable. But what about the electron on the moon? So I didn't touch it. I didn't interact with it. But somehow it suddenly changed the state. So basically, that's the description of quantum physics. And that's what Einstein saw a problem in here. So that kind of appears to be in contradiction with the special theory of relativity, in contradiction with the locality principle, actually, right? Something that you do in here suddenly changes some other state. So if it's not on the moon, just at the edge of the galaxy, there's going to be a problem. What is interesting in here is that if I make a different measurement, let's say that I measure the spin along that direction, in which case the collapse is going to occur to either to that state or that state, or the other one, right? I have just pictures for all of them. Okay? So by choosing in which direction I have to, I measure the spin orientation, I can change the spin orientation in here. I mean, what is wrong in here is there are actually many things that you can object. I think what's important in here is this locality thing. All right. There's something called the locality principle, right? Locality principle says that if you make a change in here, if you do something in here, the effects of that thing basically first changes only the things around here, and somehow it just, with some certain speed, it just propagates in space, right? So something that I do in here cannot suddenly change something elsewhere. So if you're in a pool, for example, if you just create a wave at one corner, there's going to be a wave produced in there, and that wave is going to propagate to the rest of the pool. And so as a result, that's essentially what the locality principle says. We can explain everything with locality. I don't know, the gravitational force, for example, right? The Earth is not applying a sudden, I don't know, instantaneous force on the moon. The Earth is, I don't know, is just bending the space-time according to general relativity. I mean, we have a local explanation for everything in physics. But this entanglement thing, so that appears to be contradicting with this locality principle. All right, I'm not going to. But this is important, right? It appears to be against, but by using entanglement, we cannot communicate faster than the speed of light. That's something that can be proven, right? So as a result, this appears to be a problem, but it's not a problem on the physical side. It appears to be a problem of the theory, actually. Okay. At the end, what Einstein said, based on this argument, is that by locality, by a local measurement, a measurement done in here cannot possibly affect the other particle if it is too far away. So that's nonsense, he says. Essentially, right? That's not these are not the words he uses, but that's essentially what he says. And so therefore, he concludes that somehow each particle must have known which result they would produce if they are measured. Okay? All right. That's one of the things that it's hard to actually explain. So what happens that I measure the electron, the spin of that electron. Somebody else on the moon must measure the spin of the other electron, right? When both measurements are done and they compare the results, they are going to see that both of them are antiparallel to each other. So whatever the orientation they choose for both measurements. But there has to be two measurements in there, all right? So what Einstein is saying is that these electrons must have somehow carrying some kind of an extra information which tells them that when they are measured along this direction, this electron knows that it will come out in the up state, and that electron knows that it will come out in the down state. And this possibility was never possible in this kind of a situation. So this has never been possible, actually. When we are talking about a single event, only one outcome was possible. So as a result, there was a real direction that we can talk about before the measurement, actually. And after the measurement, this reality is actually what appears in the experiment. All right, I explained it in a very complicated way, right? He says that, well, there's a reality to the direction of the spin. And when we are measuring it, we are just finding out this one, right? So that's in a way, the claim. All right, do you have any questions in here?
Professor.
Yeah.
So how does spin value affect the particles' behavior?
Spin value affect particles' behavior? What do you mean?
The orientation. Does spin value affect the orientation of these observations?
Again, I don't understand. I mean, we are talking about two different experiments in there, two different measurements. So in quantum theory, it's basically the outcome is completely random. But they are correlated, right? So the measurement done in here and the measurement done in here, they have to be correlated with each other. So the spin is actually an intrinsic property. It has nothing to do with this, I don't know, the motional state of the electron.
Professor,
Yeah.
I have heard about that one of the philosophers who
Who
has influenced Albert Einstein was David Hume.
David?
David Hume. He was thinking that even the nature of laws can be considerable and we can suspect about them. In our century, do you think that the philosopher can inspire physicists like last century or previous?
Let me answer it at the end, all right? Because I don't understand philosophy, so it's not something that I can answer right now, all right? So let me answer it at the end, so perhaps I can understand it better. Okay, so the question is it possible to find a better theory than quantum theory? Especially the one that's realistic, and it must also be local, all right? So we are actually looking for a theory. It has to be realistic because otherwise this entanglement, the entanglement is actually a big problem in terms of explaining it actually. So the question is, can we find a better theory? The problem is that quantum theory is actually very successful, so that's one of the problems. And so as a result, we don't want to actually get rid of that part actually, right? So as a result, we need to find a theory, another theory, which is realistic. It should have realism in it. It should be local, and it should have the same predictions as quantum theory. So 3 properties must be satisfied. So now I can answer your question. Can we explain double slit experiment with a realistic theory? All right, that's the theory proposed by de Broglie. So he actually proposed this in the Solvay conference, but somehow nobody takes him seriously, right? Only like, I don't know, 20 years later, David Bohm actually took this theory and he actually developed into a full mathematical theory, right? He says that, well, it's called the pilot wave theory, or kılavuz dalga in Turkish, right? He says that, well, it's not just a particle. There is actually both particle and a wave, right? So particle and wave actually move together. So it's not just particles. So somehow probably macroscopically we only observe the particle and not the wave, but both of them are present, he says, right? But the wave is actually a guiding wave. So the particle essentially moves only to places where there's a wave. And so the wave guides the particle, yes. So as a result, in this double slit experiment, for example, both the particle and the wave is actually passing. Wave is passing from both of the slits. And so therefore, wave shows this interference pattern. So therefore, there are like dark fringes in here. Particle, however, particle is just a particle, right? It passes from one of the slits, for example, the left or the right. So there's a reality actually to the slit where the particle has passed through. That's okay. Moreover, the particle doesn't visit these dark places because it's just like a surfer, right? The particle can only be at places where there's a wave. There's no wave in here, so the particle doesn't hit that to that point. No wave also in here. I mean, we would actually see the same behavior for a surfer, right? If you have a surfing wave in this kind of an experiment, for example, we will notice that the surfer actually, is going to end up somewhere in here and not in here, right? So that's the realistic explanation, right? So, but this is a different theory. It says that, like for example, in this atomic picture, there is all a cloud, this 1s wave function or something like that, a wave, but there's also an electron with a definite position. It also has a definite velocity. So when we are measuring the position of the electron, we find the electron in here, where it is before the measurement. But yeah, both of them are somehow working together. So this is a different theory. If I want to use this theory, I have to use not only the wave function, but the real position of the particle in my equations. So probably both of them are going to have some kind of equations of motion or something like that. Yes? No questions? No, all right. Yeah.
But this doesn't explain why, when we measure it, it doesn't show, it doesn't make an interference pattern. when we measure it, there is no.
Well, yeah, when you measure it, you find the particle in here. Yeah, I mean, in that case, probably you have to also introduce this collapse of the wave part too. All right, but at least for the particle properties, it introduces the, I mean, it gives some reality to the meaning of the position of the particle. So it makes this real, right? So this is a realistic theory. As far as I know, it has exactly the same predictions as quantum theory. Right? You basically reproduce all the predictions of quantum theory. So these are actually equivalent theories in a way. I mean, equivalent meaning this, actually. You can predict anything. I mean, if you want to do an experiment, let's say, both of them actually predict the same outcome for the experiment. Right? That's what I mean by equivalent. They have same predictions. But of course, they are different theories. The problem with this theory is that it's not local, right? Yeah, it's not a local theory. So in here, if you do some kind of a measurement in, I don't know, do something with this electron, some other electrons on the moon, they are going to get affected. So probably you can even send messages faster than speed of light by using this kind of a theory. Probably, but I'm not sure. I mean, I didn't actually really study that theory. I just know it in a rough way. So as a result, I don't actually have much idea. So there are three conditions that an alternative theory must satisfy. It must be realistic, it must be local, and it must have the same predictions. Can we find a theory satisfying all three of them? And John Bell in 1964 said, no, we cannot find. So a local realistic theory says, he says, it should have different predictions than quantum theory, whatever they are. So there's no specification of which theory we are talking about by locally realistic. So it basically, you can think of it as a class of theories, actually. He says that all of these locally realistic theories satisfy some kind of a relationship called the Bell inequalities. They have to satisfy it, but quantum theory violates it. And the question is whether nature actually violates these Bell inequalities, because they can be tested. Right? Okay, so it's like 7:30, right? All right, let me not deduce it. Right? But let me just be quick, actually. So this is the form that's actually developed later. So its original Bell inequality is actually quite hard to understand. This is easier to understand. It's Clauser, Horn, Shimony, Holt. Clauser is the first person who got the Nobel Prize. This is just a theory paper. But I mean, the inequality is actually quite easy to understand. What we are doing is like we are measuring 4 different quantities. Well, 2 quantities of that particle. These are 2 particles in some kind of an entangled state. Which particles, it doesn't matter. You can think about the electrons, but the real experiments are done with photons. I'm measuring 2 possible quantities in here. We show them by A1 and A2. 2 possible quantities, B1 and B2 in here. Both of them, we are just assuming that they have only plus and minus 1 values. Like the spin, for example, right? Spin up is +1 and spin down is -1, for example. They have to be compatible with each other, incompatible with each other, A1 and A2. So you cannot measure them at the same time. So you either measure A1 or A2, but not both of them. And similarly for this one in here. So somebody measures A1, let's say, and somebody measures B1 in here. So actually different people should do this because these are too far away. So they say that Alice measures A1, Bob measures B1 in here, and they somehow share their results at the end. So this is kind of the experiment. So the difference between realistic theory and quantum theory is that quantum theory says that these quantities are uncertain if they are not measured. If they are measured, only 2 of them can be certain. The other 2 has to be uncertain, right? But the realistic theory says that even if you don't measure them, they have meaning. So all of these 4 quantities have some certain values. So as a result, in a realistic theory, I can talk about this kind of an expression. It's just a mathematical expression. And then I can say that, well, this expression is either +2 or -2. Okay? So the realistic theory somehow goes further, actually, but the quantum theory is just stopped in here. So this says that, well, the equation above is meaningless because at least 2 of these numbers should be uncertain. Nobody can write down this kind of an equation. That's what quantum theory says. Realistic theory says, well, we can write them down and we can actually argue that this is equal to either +2 or -2. I'll explain why. And so therefore, their average value should be between +2 and -2. So that's the Bell inequality. Okay? Why it is +2 or -2? Just remember that B1 and B2 are +1 or -1. So as a result, either this one or the other one should be 0. One of them is 0 and the other one is either +2 or -2. And what we do is like we just multiply one of them with +-1, the other one by +-1, but only one contribution is coming from one term, so this is +-2, right? This is more or less, I mean, the inequality is something like that. It's deduced from here. So after taking the average, if a quantity is either +2 or -2, its average should be between these two values. Okay, all locally realistic theories must satisfy this inequality, but the quantum theory violates. Its maximum value is about like, it's 2√2, right? It's 2.83. Okay, so let's talk about this Bell experiments. What we do is this, right? I mean, this is the correct way of doing the experiment. We have a source in here of entangled particles. It produces 2 entangled particles and sends them in different directions. One to Alice, the other one to Bob. Alice has some kind of an experimental arrangement in here, but she has to make one of these 2 possible measurements, but she chooses the measurement randomly at the instant when the particle reaches to that location, okay? She chooses what to measure randomly, and then after that, of course, she measures the value. And Bob does the same thing, actually. And it is important that both Alice and Bob, they make their decisions at the same time, and they have to take their measurements at the same time, right? So this is actually done by some kind of a device. This choice is actually made by some kind of a device. And after the choice, of course, there are some detectors in here which actually does the measurement, right? It has to be done like that. And then after that, there's some kind of a, I don't know, information gathering computer in here, and that computer basically computes the averages of all of these quantities and add them up and then tries to see if the inequality is violated or not. Okay? So this is the first result that basically done by Clauser in 1972, right? That's actually too old. That's basically a verification that the nature also violates Bell inequalities, just like the quantum theory. Which means that locally realistic theories are not able to describe the nature. Quantum theory does. So this kind of tells you that there is no reality in the way that we understand it, right? This actually settles this philosophical question. How did they obtain the entangled particles? So they actually use some kind of a particular atomic transition. It's called a cascade transition. So there is some kind of a atom in an excited S state. So first it makes a transition to some kind of intermediate P state emitting a photon. And then after that, it immediately does a second transition and emits a second photon. So they are they have different frequencies. So usually you can separate them and then send them to different places. In any case, S state is a state where the angular momentum is 0. So the atom has 0 angular momentum before and after sending the photons, but the photons have angular momentum. So this kind of tells you that this photon and that photon, they should have opposite angular momenta, which says that the polarizations of these two particles should be somewhat correlated. It appears that these two photons are entangled, right? I mean, in all of these kind of situations, you produce an entangled set of photons. That's the old technology, actually. But in any case, that's the one that's done by us. So Alain Aspect did the same experiment, but with the, with the correct way, actually. It is important that the local measurements are randomly chosen. Clauser's experiment didn't do this. He just somehow arranged the setup in a certain way. So he measured only a certain quantity. So the idea in here is this. These are called loopholes, actually. If you arrange your setup in a certain way, then it is known what you are going to measure, right, before the particle reaches there. So perhaps they suspected. Perhaps the particles somehow realize this, and then so they can arrange themselves in a particular way so that, or perhaps they can communicate with each other. And so as a result, they can perhaps show the correlation like that. Okay. In the real experiment, you don't actually give any chance to the particles to communicate with each other. You do both choices at faraway places at the same time and do the measurements at the same time. So when you finish the measurement, the particles do not have actually any possible communication between them. So this is just some kind of a logical loophole. That's not actually quite important. As far as people are concerned, Clauser's 72 experiments somehow settled the question once and for all right? But they have repeated these kind of experiments under different conditions. The last one is in 2015. You actually see this expression many times. It's called the loophole-free Bell tests. So these are actually done in 2015. So as a result, modern experiments actually continue. They have done this with large distances, like over 200 kilometers, for example. And sometimes they can do these kind of experiments between ground and the satellites as well. Why do we do this? Nowadays, why do they do these kind of experiments? This has something to do with the quantum technology that people are trying to develop, quantum computers, quantum networks, and things like that. This technology is actually being developed for that purpose. But this technology can also be used for doing these kind of precision tests. So as a result, that's the reason why people are doing this. So in any case, this is something else. It's called the parametric down conversion. There are some certain type of crystals called nonlinear crystals. They somehow show some kind of a nonlinear behavior under electric and magnetic fields. What happens is that when you actually send some kind of the process is this. When a photon with frequency nu enters into the crystal, by a process, this photon is divided into two photons. By conservation of energy, this frequency sum rule must be satisfied. But this can only happen inside a nonlinear crystal. It's a very weak process, so they actually use a very strong laser in here, and they get two weak. One of them is called idler, and the other one is called signal. Two weak beams in here, actually. All right, these kind of pictures are actually used a lot. So nowadays, this is the entangled photon source, right? That's the one that people use. Emre Yüce, for example, has one of these crystals, and he's doing, some experiments with these. If you are interested in, you can actually. All right, this is quick. Okay, so this is something else, but this is a little bit. You can think of it like the Bell inequality topic is somehow has evolved to this. So there are no entangled states in here, but there's a different concept. It's called contextuality. Right? I'll try to explain it like this, but I'm not going to deduce anything in here. So in a way, it's going to be somewhat quicker. So if there's some kind of a quantity, when we are measuring this quantity, we can measure it in many different ways. And each one of them is called a context. So I can, for example, I can measure this quantity alone without measuring anything else. This is one context. I can measure A1 together with it. I can measure B1 property of the next particle. That's also another context. Or I can measure A1 in here and measure B2 in there. So in any case, there are actually different ways of measuring, taking a measurement, and each one is called a different context. Okay? So in a realistic theory, that's only the classification only for realistic theories. This is not applicable to quantum theory, right? For realistic theories, just keep in mind that in realistic theory, when you measure something, you get a value that's already determined. Without actually doing the measurement, you can still talk about the same value. So the question is, do you get the same value in this context and in that context? Do you get the same value for A1 in all of these contexts? So if the value that you get for a quantity does not depend on the context, then we call these theories as non-contextual or context independent, or in Turkish bağlamdan bağımsız. But if the theory is strange, the value that you are going to get will depend on the context. Right, I mean, we can also talk about this in terms of people. So probably, I think my Turkish is not that good actually. I think we call these kind of people like kaypak people, right? When you ask a question, for example, the answer they give to you depends on the context that we ask. For example, the other people around us, for example, right? So if that person gives a different answer to the same question under different conditions, that's a kaypak person. And these are actually kaypak, in a way, theories, realistic theories. We don't want them. Einstein wouldn't want these, actually. So these are contextual theories. We can just throw them away. So there's no meaning to talk about these kind of theories. But the context-independent, non-contextual theories, so these are honest theories, if you want, just like the honest people. They will answer the same question in the same way, independent of what the context is. All right? So there's actually a very nice theorem that compares these non-contextual realistic theories in terms of predictions with quantum theory. It's called the Cauchy-Specker theorem. It's 1967. Apparently Bell found the same result in 1 year before. It basically says that these good theories, these honest realist theories, have predictions which are different from the predictions of the quantum theory. These two theories cannot have the same predictions. Okay? So this is actually an alternative thing to the Bell inequality thing. However, what's interesting in here is that this has actually been done. These are philosophers actually, right? Cauchy and Specker, but somehow they studied this problem. For some reason, nobody has written down an inequality that demonstrates this until the year 2008. And in that year, there are 4 people in Bilkent University have done this important result actually. I mean, they have actually written down some kind of an inequality that also demonstrates this. So it's called the KCBS inequality. Klyachko, Muhammed Alican, Sinem Binicioğlu, and Szumowski. Unfortunately, all of this group is just dispersed now. Szumowski has died even before the article is published. Muhammed Alican was actually, he actually gave a few, this 455 in a few semesters in here. But yeah, he's outside now. He's abroad in Germany. Sinem Binicioğlu, I think she just, I don't know, dropped physics after this MS degree. And Klyachko, he was actually a nice, good mathematician in Bilkent University. He also somehow went somewhere, I don't know, retired perhaps. Unfortunately, I mean, this is a very important paper, but all the people involved in it somehow got dispersed, unfortunately. There are actually 5 quantities in there. There's no entanglement. We're just talking about a single system. It's actually a 3-level system. There are 5 observables. All of these observables also have plus minus 1 values, and they are compatible if they are next to each other. So A1 and A2 is compatible, so I can measure them at the same time. A2 and A3 is compatible. I can also measure them at the same time. So therefore, we can talk about the products of them. So any realistic theory can talk about the sum of all of these quantities. And by using this argument, you can actually show that this expression should always be greater than -3. So that's the KCBS inequality. Quantum theory says that, well, only one of the terms in these can be meaningful, the other ones must be uncertain. So therefore, this inequality is meaningless. So therefore, in quantum theory, this can be as low as -4.04 or something like that. Okay, they have done this experiment immediately after the article is published. I don't know how immediately after. Perhaps a month. I mean, it didn't wait like 10 years or something like that, just like in the original first Bell experiment. It's done immediately after, and they have verified this, right? This inequality is also violated. So that means a non-contextual and honest realist theory cannot explain the nature. Okay? So, I mean, this basically tells you that this experimental result tells you that you cannot have realism in describing quantum phenomena. That's not possible. So you either have to do this, but they don't, I mean, yeah, that's actually inconsistent with the experiments. So the honest realist theory, so they are just thrown out. And then we have this dishonest Kaypak realist theories, which we don't want actually, right?
İçten pazarlıklı da iyi hocam.
Huh?
İçten pazarlıklı.
İçten pazarlıklı, all right. All right, this is another way of actually explaining it, but in a different way, right? So it's a pentagonal dice. Think of this as a dice, all right? It's a pencil, but think of it as a dice. The game is something like that. Somebody, for example, me, let's say, just put some marks on these 5 faces in here. So the marks are either X or O, right? But I want to make sure that the marks in the succeeding pages, succeeding faces are actually different. I'll explain why. You just throw the dice, but you just look at only the top 2 faces. You don't see the other 3 faces, right? Right? There's some kind of imposing this compatibility condition. So in quantum theory, only 2 succeeding observables can be measured at the same time. You cannot measure the other 3 in that measurement. So that somehow imposes this condition. So you just look at only the top 2 faces, and it's illegal to look at the other 3 faces, right? And if you see the same sign in here, like both of them are X or both of them are O, you win. Otherwise, you lose. And the question is, what's your probability of winning? Now I can use the board. So that's something that's quite easy to see, actually. So if I try to put different marks on succeeding faces, at some point I just find a place where, I mean, these 2 symbols should be the same. Okay? So as a result, there should be at least one neighboring faces in here where the symbols should be the same. Okay? So as a result, when this face becomes up, in that case, you are going to see double X. So that has a probability of 20%. All right? So that's a realistic dice, however. In a quantum dice, the probability is around 10%. That's actually quite hard to understand from, I don't know, from our minds actually want to actually see this realist picture. So as a result, this also is something that's quite hard to understand. There is actually another version. So we have done some kind of a work in here. So this is usually called the, what's it called? I forgot the name, sorry about this. But this is a logical form. There is actually a different quantum state. I can actually make this system go into that particular state where I can actually make all of these logical assertions to be true for that particular state, right? So the first one means that, well, if I measure A1 and A2 at the same time, or I don't know, whenever I find A1 to be equal to +1, I always find A2 to be equal to +1, right? That's some kind of a logical statement. You can actually express it in different ways as well. So I can, by doing several experiments, I can verify that this is definitely true for that particular state. And I can do the same thing for all the other statements. So each one of them makes sense, but when you combine all of them, our classical minds, our realist minds somehow find some kind of an impossibility. So A1 being equal to +1 implies A2 being +1, which implies this to be plus, which implies that to be plus, which implies that to be plus, and finally we reach to the conclusion that A1 has to be equal to -1. All starting with A1 being equal to +1. All of these statements are true, but at the end we reach the conclusion that A1 is equal to -1. So that's actually a contradiction, right? But somehow this kind of a possibility exists. So there's some kind of a non-zero probability of finding A1 to be equal to +1, and all of these things are definitely true. The problem in here is this incompatibility thing. So you can talk about the truthness of this statement and that statement, but you cannot talk about the truthness of this statement and that statement together. Why? Because A1 and A3 are incompatible. You cannot measure them at the same time. So the quantum theory rejects discussing the truth of both of these statements at the same time. That's kind of strange, actually. I wonder if this thing has some kind of a I don't know, macroscopic demonstration with the usual, I don't know, logical statements that we have. Çay. Yok getirme, yok. Çay. What is next? What's next is, oh, it will be midnight in a moment. All right, so like since 1980s, we are actually within this process which is called the second quantum revolution. Basically, these are some set of technologies, all are different technologies actually, set of technologies where we can manipulate the quantum state of an individual system. So up to now, it has always been like we're talking about the measurement of like the double slit experiment, for example. You do the experiment on many particles, millions of particles. Now we are talking about the manipulation of a single particle. So we are manipulating the quantum state of them. Quantum cryptography is a very important thing. This entanglement has a very nice application in quantum cryptography. If you want, I can explain. Quantum computing is another one. You have heard this most definitely. It is still being developed, but it appears like we are like close to the final development, like perhaps we are only 20 years away or something like that. Quantum metrology, like building very, I don't know, accurate clocks and things like that, or accelerometers and things like that. Especially for military technology, this is very important. There's, for example, quantum radar in it. That's very strange. It actually uses these entangled states as well. So you're building a radar with a very weak signal, but somehow you can detect planes. And there are these quantum networks and so on. Yeah, I don't know. I cannot probably I cannot count all of them. So there's this idea of quantum information. So you can use any quantum system as some kind of a memory. So for example, a two-level system like the spin system with spin up and spin down states, they can be in these two possible states that we call as 0 and 1. But they can also be in states of superpositions of these states, which is something which is hard to imagine, all right? So it's like the double slit thing again, right? So we're talking about the superpositions of these. So it appears that we can use them in many different ways, and quantum information theory basically is about the manipulation of this information and how we can do it, I don't know, how we can do what. So this is an important result in like 1982. It's called the no cloning theorem. It essentially says that you cannot copy that information. You cannot make a copy of a quantum information stored in a quantum memory device if you don't know what that information is. So an unknown quantum state cannot be copied. That's the statement. But yeah, whatever. I mean, basically, that's kind of strange as well, because you can easily copy classical information. You can make millions of copies of movies, for example, right? Probably you have this experience as well. But a quantum movie, no, you cannot copy it, right? So it should have only one copy. So as a result, if you want to send a quantum particle and its, I don't know, information content to a faraway place, you have to send the particle physically, all right? That's one way. But in 1993, they have found a different way. It's called teleportation. By using entangled states, you can actually transfer the state of the particle without sending the particle. It is just like the teleportation in science fiction movies. In Star Trek, for example, you are familiar with this teleportation. It is actually familiar in some respects, right? I can explain it if you want, but this is basically the teleportation of the state itself and not the matter. But it can be done. So Zeilinger has done this experiment for the first time. So that's the reason why I am explaining it. So there's some kind of a all right, since I have started with this, let's finish this. So suppose that you have a particle C, for example. It's a memory device. It is in some kind of an unknown quantum state. You don't know what the state in here is, right? It is either 0 or 1 or a particular superposition of 0 and 1. And you would like to send this particle state to here. So suppose that these two are in Ankara. This is in Bursa. Alice is in Ankara, or Ali. Bob is in Bursa, or Berna, or whatever, right? In any case, you would like to send the information only. As I said, you cannot make a measurement in here, or I don't know. If you make a measurement, you are going to destroy this information completely. You don't want to do this. You cannot make a copy of this thing. Yeah, whatever. I mean, so as a result, you have only single copy, and somehow, without destroying it, you want to end up with a final situation where this state is in here. Okay? So this is the protocol. So first we should have some kind of an entangled pair of particles. One of them is in Ankara and the other one is in Bursa. We should have entanglement to start with, right? Yeah. The protocol basically involves something like that. You just take some kind of a measurement on these two particles. This measurement destroys the entanglement. So the entanglement is gone. It's consumed, actually. It's gone. And then there's some kind of a result in the measurement. So it's actually a 2-bit information in there. You just send it by, I don't know, using telephone, for example, to Bursa. And Bob in Bursa actually does some kind of a process that involves the information that he received. At the end of the process, the information is there, right? It is some kind of a transfer of quantum information, which kind of appears, I don't know, it's quite unusual actually. right? Without destroying the information and without sending any particles, somehow you were able to send this information, quantum information, to there. In some certain respects, this actually is quite like the teleportation in the science fiction movies. Technologically, it's important in quantum networks. We are actually using this teleportation to send some quantum information to a faraway place. Yeah, that's very important actually. And Zeilinger has done the first experiment. There's some kind of a race actually to do these kind of experiments. Whoever does it for the first time, they get the recognition actually. It is in 97. Like 93 is the proposal of the idea of teleportation. 97 is the first experiment. Well, he has done this experiment with photons, obviously, right? Because, I mean, if you want to send the quantum information to a faraway place, you have to use photons only. I don't want to explain the experiment because there are some kind of imperfections in there, but that's not that important. What's important in here is that he actually demonstrated this strange phenomenon, right? Again, since I'm not an experimentalist, I don't actually go into these kind of details. So let me say one more thing, one final thing. I believe that this is the guy that actually has changed everything. So, I mean, he actually was able to show that you can resolve this philosophical problem that I mentioned at the beginning by doing an experiment. So I think his was the most critical experiment. And because of that, he actually deserved to win the Nobel Prize. But unfortunately, the prize is not given posthumously. So I think in 1990, it was actually too early to give the prize. But in any case, it is a late prize. It is given to somebody else, but at least it is given. So I think that's important. One more thing, all right? You know about our top looks, right? Thank you very much for people in physics society and QTurkey student branch. I don't know if they want to explain themselves. So thank you very much for bearing with me for 2 hours. I am sorry about this thing. I have given a talk about the causality. It was also 2 hours long. I think the whole thing is perhaps can be explained in like 50 minutes probably. So if you didn't understand anything, just call somebody else. Probably they can explain better.
Before we go into the tea session, if you have questions, now is the time.
There's a tea session which
yes,
we discuss.
There is a tea session, but before that, if you have questions, our professor can answer them. So.
Yes.
The first example of development quality that you gave with the A1, A2, B1, B2, as far as I could understand it, seems to immediately follow from the realist argument.
Yes.
But I don't see where the locality plays a role. In that
Locality, huh? Locality. If I measure this B1 should be the same as this B1. So the argument in here is this, right? The B particle perhaps may understand that the other person is measuring A1 or A2, and as a result, it changes the result that it should give when B1 is measured, right? So it is possible under these kind of situations that this B1 is different than that B1. I mean, this is actually some kind of a logical thing, logical loophole actually. So we don't know any mechanism like that, but this B particle might actually sense what is being measured for the first particle, for the A particle, And depending on what is measured in there, it can change the its value that it would produce in here, right? Because of that reason, it is important that both of the experiments are done at the same time so that they have no way of communicating. And this local theory also tells you that when you are measuring A1 in there, it doesn't instantaneously affect the value that you would get for B1. So as a result, this B1 is the same as this B1. Yeah, it's a very, I don't know, complicated argument, but it is necessary. So it is in principle possible that for non-local realistic theories to violate this inequality and describe the nature, but this is something that we don't actually want. Einstein also doesn't want that. Yes?
When you first introduced contextuality, you hinted a relation between entanglement and contextuality. What is the relation between
For contextuality, you don't need entanglement. Because in here, you need the locality argument that one measurement doesn't affect the other one. You're using that locality argument. So as a result, you have to have some kind of an entangled state. In the contextuality, this is something that you accept. You're accepting that when you're measuring, for example, I don't know, A1, let's say, together with B1, or A1 together with B2, you get the same A1 in there. So that somehow is within the assumption of contextuality. All right, I mean, these are actually quite difficult things to explain, right? There are actually some complicated arguments in there, somewhat complicated, so it's not easy to explain. Yes?
I didn't understand the idea behind the quantum teleportation. I mean, we didn't use the idea of entanglement. We just some sort of like a great entanglement, but why it is called quantum then? I mean, I didn't understand that part.
You need a priorly established entangled state before you do a teleportation.
What happens if I don't do this?
That means that you can actually clone the state, so that's not allowed. It's like no cloning theorem. If somehow, without using this entanglement thing, you have done this process and at the end you transfer this state to that location, you can repeat the argument. I mean, what you have done is essentially you have sent like classical information in there. So anybody with that classical information therefore can produce the same state in here. So that means that you can make copies, other copies as well. So that's kind of against the no cloning theorem. All right. I mean, all of them are actually kind of connected with each other. So it is essential that there has to be some kind of an entanglement in here, and then you somehow, I don't know, use this entanglement in this local measurement in here. All right.
I mean, after the measurement, didn't we break the entanglement?
Yes.
So what's the use of entanglement in the first place?
But how did you break it? You made a measurement in here. That measurement made sure that this particle collapsed into some particular state. So in that particular state, there's this information of psi hidden in it. Okay? So no, I mean, definitely there are some details in here. So, I mean, this is also essential. You need to send some information, otherwise you can violate the causality principle of special theory of relativity, for example. Because collapse is instantaneous, right? So there are these kind of details in here, which is actually kind of important. Perhaps I can explain it later, why all of them somehow has to be consistent with each other. But I mean, you can actually use lots of different physical arguments in here and kind of justify all of these. Okay, so that's my suggestion, for example, how the teleportation might be useful. So, for example, the nearest star is Alpha Centauri or one of them, right? Which one? Yeah, whatever. It's 4 light years away, right? So to send a spaceship over there takes, I don't know, thousands of years perhaps, right? We cannot have like fast spaceships. But we can teleport someone there. I mean, if we can do this teleportation, the only thing that we need to do is to send this classical information, and somehow we have to establish some kind of entanglement between some particles between here and there, right? If we somehow send some kind of a device over there that does this teleportation on that side, and we have a human in here, we can do this thing. I mean, there will be lots of information that we have to actually produce as a result of that measurement and send over there. But what we need to do is to basically send this information over there electromagnetically, which reaches to that star in like 4 years. And after 4 years, they are going to reconstruct that person over there. So as a result, travel to the stars can be done actually with the speed of light, by using this process, for example. Unfortunately, right now we can do this only for single particles. I don't know, in 20 years perhaps we are going to do it with molecules and something like that. But for humans, probably it's going to take much, much longer to achieve this. But I mean, in principle, this is possible, for example. I mean, we don't have to use spaceships that travel for a long time. We can just use teleportation to travel between, I don't know, between here and Jupiter as well, for example. The travel doesn't need to actually take that long. Okay? I mean, this is one, I don't know, science fiction application of teleportation. And for me, this is also kind of interesting as well. That's too much, yeah.
If we accept there are multiverses.
Multiverse.
Yeah, if we accept that, does entanglement let us communicate with?
The other ones? No, I don't think so. I don't think so. By multiverses, do you mean like the many worlds interpretation? Yeah, there's a problem in there that, again, this is some kind of a technical issue. Quantum mechanics is linear. It's a linear theory. If it is indeed linear as we are accepting it, then that's not possible. We cannot use any communication. But if there's some kind of a nonlinearity in the time evolution of Schrödinger equation, for example, in that case, that may be possible. It might be possible to communicate with other parallel lives that we might have, right? So that kind of a possibility is there, but it's just a theoretical thing. Yeah.
Can you maybe give us at least an informal reason for why entanglement doesn't violate causality?
That what?
Entanglement doesn't violate the second possible measurement.
So many things. When you do a measurement on this particle, the other particle collapses, right? So that's in a way, the transfer of something, some effect is instantaneously transferred over there. But there are two outcomes. You cannot pick which one comes, and each actually appears with 50% probability. So this outcome has a 50% probability, and that outcome too. The only way you can actually transfer information is that you choose something in here, right? You choose a particular information that you would like to send, for example, right? It's, I don't know, it is 0 or 1, for example. And depending on your choice, you do something else, something that depends on your choice. For example, if the information that you would like to send is 0, you make a measurement along that direction. If it is 1, then you make a measurement along this direction, for example, right? But in each case, both of these outcomes appear with 50% probability. So somebody has to do some kind of a measurement on this particle. But if the particle is either spin down or spin up with 50% probability, or this or that with 50% probability, by doing a measurement you cannot actually understand the difference. And so as a result you cannot understand which choice this person has made.
I suppose if you make it at some random angle, that information doesn't get transferred.
You what?
So if you make it, let's say, 45 degrees.
Yes. So it's always, yeah, it's always like that, all right? So the final state is definite, but you cannot understand whether the spins are oriented along the x-axis or the z-axis by doing a measurement. So that's something that you cannot understand. So somehow quantum theory hides this information from us as a mechanism, and this is the thing that somehow makes this communication impossible. So that's actually quite strange, right? So the nature, quantum theory, quantum nature somehow gives us some kind of a mechanism like that that's incredible. You somehow, by doing something in here, you can change something over there instantaneously. But at the same time, it takes away something, right? You cannot measure, I mean, you cannot distinguish this state from that state, and so as a result, you cannot do a communication. So it's actually quite connected with this uncertainty principle also. Right? Everything is somehow connected and everything is consistent. So there's one last question, let's say.
Actually, I think we can continue the questions whilst we drink the tea because it's going to get cold otherwise.
Cold.
Yeah.
Yeah, tea, yeah. So çay kutsaldır. Evet.
We can hear your answers.
Okay, çay kutsaldır. Onun için